So, yesterday, here we were. We left off looking at Oganesson, I believe. And I have no idea if that's how you really pronounce it. I've never heard that word, but that's how I sounded out. Okay. The fact that I write Z as 118 tells me what about Oganesson?
That is
118 protons. Okay. As I look at this, Z is the number of protons, the atomic number. Okay. We didn't write this out because people seemingly found it. On your table, which tomorrow I will let you guys have a periodic table open on your desk. Just so you know. You can use that. Can't turn the pages, but you can have a periodic table. Okay. For this, Oganesson, number 118. Which group? I could have guessed 18. Any idea how?
118 because of the.
Sorry. Nope, group 18. It's group 18. What's the ones digit here?
8.
8. How many electrons are here?
8.
8. Now, there are a bunch of energy levels here that I didn't draw, though, because I didn't have time to draw out the other 110 electrons and stuff. How many levels are hidden here that we just don't see?
8.
How do you make that determination?
The ones place.
So do me a favor. Find me. Group is vertical.
Oh, never mind.
These are period. What period is Oganesson?
7.
7th period. Bless you. Which means how many orbital levels or shells, energy levels?
7.
7. If we only have to see the last one, there must be how many hiding underneath?
8.
Why 8?
Oh wait, no, wait.
6. The 6 other levels we don't even bother to draw. Okay. Lewis dot diagrams. Feel okay? Feel terrible? All right. Should we do one more? All right. Cool. Ooh, I can't tell you. I can't do it this way. Let's do one more. Bless you. This time I want to do, and we're only doing main groups here, I want you to do tellurium. It's an element, so that makes sense. I guarantee it's from Latin. You are drawing me the dot diagram for tellurium. You're going to have to find out on your periodic table. You are going to have to find the symbol, all that.
What? So we have to find it.
You got to find tellurium.
Okay, so I'm gonna guess it starts with a T.
That's a good guess.
Okay, you said titanium.
It may be a metalloid. Just throwing that out there. Might be a metalloid. I wouldn't lie to you about that.
Yeah. 16. So we're just trying to do 1, 2, 3.
It is a metalloid. You are drawing me a Lewis dot diagram with only the valence shell, the valence energy level. How do you want to word it?
Excuse me. My bad. Klein, why would you do that? I didn't think it was going to be that loud.
All right, where's tellurium? Okay, so right off the bat.
Tellurium?
We haven't gotten to it yet. They are fundamentally different. These ones are non-metals. These ones are metalloids. We call them.
And then there's only 6 atoms.
So like if you look at the circuit board on a computer.
Huh? Yeah.
Okay, so here it is.
I'm pretty sure the number of what's it called? No. Or not the thing, the dots. I'm pretty sure the number of electrons is the number of.
There are 6 valence electrons. All you really have to do is tell me.
Never mind, I'm confused now.
Capital T, just that atomic symbol.
But I don't know if I'm wrong, but I think in whatever group it is, you choose the ones place of that number, whatever group in the vertical, and then the ones place of that, and then you put that as the dots as the electrons.
So 6.
So 6.
And then how many
That's why I
electrons
thought it
was that one
6.
digit?
It's 16. So I thought there's 6 electrons because it's the.
So find the group, Akis, and then the group, the ones digit.
Mr. Holloway, am I right? Okay.
So there's 6 then.
All right. So tellurium, right off the bat. I don't expect like scavenger hunt all the time, but what is the atomic number?
So
It's
52. That means it has 52 what?
electrons.
Protons. Probably electrons realistically, but I only care about protons right now. Okay. With that, which group?
16.
Group 16. Which period?
5.
All right. So that means the highest energy level is 5. There are 4 more underneath it that we don't even have to see. I only need one more piece of information. What's the symbol for tellurium? So here we are, Te. This is my nucleus and those first energy levels that we don't care about. And then out here, I only have to show that very outermost level. And gosh, it's a 10 right here. And what's the ones digit?
6.
So let's put 1, 2, 3, 4, 5, 6 electrons here. We're done. That easy. That easy. Now, we'll use this again later, and we're going to expand on this. So we have dot diagrams right now. Okay, for these, I'm okay with where we're at, but there is another way to build these as well. So I'm going to show one alternative of just a different way to do it. Are you ever going to find something in a group higher than 18? So we're going to connect this. You can write this if you want, but I need you to at least hear it and internalize it. We're never going to have anything more than group 18, which means at most, how many valence electrons are even possible?
8.
At most, every element will have 8 valence electrons. At most, elements, or atoms if you would rather, have 8, or have a maximum of 8 valence electrons. Okay, you just can't make it bigger than that. Maximum of 8 valence electrons. Okay. Now, it turns out that sometimes, even though this is way simplified to draw the element and the circle around it, there is a more concise and easy way to do it. So, yes, sir.
Will we ever have to do like a full extended thing?
What do you mean by full extended thing?
Like when it has multiple rings around it?
If I make you do that, it would be period 2 or 3 at the very highest. Yeah, I will not make you go out to 7 levels. Not a chance. Okay, so as an alternative, we get a simplified version of these. So we have Lewis dot diagrams, which these ideas are nice. It's like a Bohr approach to it. But we have these simplified dot diagrams. Okay, for this, these are nicer and easier to draw. Let's take a look. They're super similar. I want to see if you guys can help me make sense of what I'm doing. Rather than me saying, here's how it works, look at it. I want you to help me out here. Give me an element that's in a main group. So nothing between 3 and 12. Any element, don't care. Pick one. Beryllium. Okay, 4. Beryllium. Here it is. Example of these. Here's beryllium. Now, beryllium is element number 4. It's in group 2, period 2. Group 2 is what I care about. How many valence electrons? If it's in group 2, it has to have how many? 2. Okay, so check it out. Rather than drawing that whole big ring, which is nice, we can start to think about the atom. It is pretty common to take just the symbol, and then, do you guys agree, don't draw these, but there's like 4 sides to this, right? There's a above, below, right, and left. Okay, everything can be put into a box like this. Every letter, like whatever. Okay, how many valence electrons? 2. Check it out. I start by convention here on the right side, and then I feel it's more natural to go counterclockwise for some reason. How many dots are around this thing?
4. Oh, wait. 2.
What do you think those 2 dots represent? Valence electrons. Is this easier than drawing the circle and the orbit and stuff? Okay, let's do one more. And then I'm going to have you guys do a couple. Let's do neon. So I'm going to scoot this over. We're doing neon. And I'm just going to start with the symbol, Ne. Okay, neon is where on the table?
Neon, that's 18.
It's number 18? Group 18. That's what I care most about. Okay, the fact that it's group 18 means it has how many valence electrons? 8. So check it out. How many little dots am I going to put around here? 8. And I always do it as follows. I go 1, 2, 3, 4, 5, 6, 7, 8. 2 on each side. Now, we will use this starting in chapter 17. It makes it really clear where things can or cannot join on. We don't have to arbitrarily place them on a circle. We just assign them to each side as needed. Okay, I want you guys to do a couple more for me. Is it obvious how I'm getting these?
Yeah.
Okay, if anybody struggles with it, who could you ask? Me, your partner, not ChatGPT because I don't know if they're going to understand it. I don't know. Cool. All right. You guys are going to do 2 of them. Shout out main group elements. Sodium, I like it.
Phosphorus.
Iron's not main group.
Wait, what's the
Phosphorus.
Oh, never mind.
I heard yours, but I didn't get it. Cool. Yep. I want you guys to do the simplified dot diagrams for sodium and phosphorus.
Wait, so just do what we just did?
Yep, just the dots. You don't even have to draw the circles.
Wait.
Phosphorus is on the right half of the table.
I thought it could only be through 12.
So we never will do this for now for our purposes. We will never do it in anything in group 3 through 12.
Oh, never.
Never group 3 through 12.
Wait, what's the other one? Phosphorus and...
Sodium.
I think there's another
Wait,
side. Wait, what side is it on?
Does that mean that everything in group 1 only has one dot?
Everything in group 1 has 1 dot. Exactly. Yep.
Why?
Are you on your phone? Are you on your phone? You should just bring it up here so we don't have to fight it. Okay. All right. What are we at? You guys get it?
Wait, hold up.
All right. All right. Oh, wait.
It has what?
Bro, it has. Where did I lost it?
Okay, I'm going to roll through here.
That's fine.
Drink of water and then I'll roll through.
That? Or is this supposed to be English?
Show me your sodium and your phosphorus. Yep, so show me your dot diagram. No, your dot diagram. Where are you writing?
I did it on Jonas notebook for some reason.
Too much. Why do you have so many dots around it?
15.
Too much.
Oh, 5.
Okay, doing okay? So what is So one dot.
Whoa, no.
Yay, nay. I'm sorry. Have you found sodium? Have you found sodium on the table? Which group? That's period 3. Which group? Okay, so what's that number? 1?
Yes,
1 dot. Just 1 dot right there. You got it. Cool. Find your phosphorus. Yep. You have yours line?
Wait. Oh, fuck.
But how much DoorDash are you about to do with including?
Why is it got it?
As much as I can.
I got it.
I don't mind.
She asked for help.
Yep, electrons come from the group. The levels come from the period. Okay, so checking these out. These are super fast, I hope. Okay, sodium is group 1. Don't even care what period it is for this. 1 dot. Boom. We got it. Okay. Phosphorus, which group? 15. And the 1's digit is So check it out. 1, 2, 3, 4, 5.
What if it has like, what if it's in group 5?
If it's in group 5, it is a transition metal, and it gets weird. Cool. Now, remember, yesterday I made a claim about some of the groups. We'll dig into it more. These feel pretty easy, I think. And if they didn't a second ago or they don't now, please let me know. I will clear it up a step further. But doable, I hope. I took attendance, and I'm pretty sure that I'm good. Okay. Now, some groups have special names. Okay. I'm not going to expect you to memorize like all of these, but there's a couple that are worth talking about. Group 1. I think Liam asked a second ago. If we look at group 1, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. They're all in group 1, means all of their dot diagrams have how many dots? 1. All of them have 1 valence electron. Now, I made a claim yesterday, I just don't recall if we wrote it down. Things are stable, and like truly stable, and they have how many valence electrons? Not 1. Check your notes. I think we said something about stability. Jonah, I meant to say yes after I saw your work. Please take your own notes too. Like you asked if you could go. I'm fine with that.
Thank you.
Okay, when their valence level is full. And a moment ago we just said because group 18 is the biggest group you're ever going to get to, a full valence level would have how many electrons? 8. 8 is stable. Okay, now, if we start to think about why, all of a sudden these things start to make sense a little bit. If you want to get to 8 from either of these situations, and I know it seems strange, there's 2 options. If I recognize that, hey, sodium being in group 3, it has 2 completely full levels underneath of it. Are you guys okay with that? Sodium, and I'm going to draw this one out for the real diagram because we're going to connect something. You do not have to sketch this, but I need you to at least listen and pay attention, okay? Sodium, it starts with a nucleus. I'm just going to call this nucleus. Its first shell has 2 electrons. The next shell has 8 more, and then the third shell will only have 1. Okay, this is the Bohr model of sodium. A full shell here with 2. That's the only place it happens. This one's full with how many? 8. 4, 5, 6, 7, 8. And this one has 1. Okay, now, right now, is its outermost shell, its valence shell or level, is it full? No. To make that third level full, what would you have to do? You would have to add 7 electrons, right? So let's pretend that you are going to be the one adding and removing electrons, and they're bags of concrete, so you're going to have to carry them, and it's going to suck. You could carry 7 more bags of concrete or 7 more electrons and add it and fill that level up. Everybody agree with that? If I added the 7, we would be super stable. Okay, alternatively, is there another way that I could make it so the outermost shell is full, but I don't have to carry 7 bags of concrete? So you say switch them. Just so it's just my electron. Like if we have, let's say that sodium atom is in Miss Eustace's room, and you guys need to make it stable, and the electrons are bags of concrete. You can carry 7 bags of concrete all the way down there. That's going to be a lot of work. It's going to be hard, right? But all I require is the outer level is full. Alternatively, instead of filling it up the third level, if we take one away, do I have any electrons in my third level anymore? So that level just essentially disappears. And that's a weird idea, but check it out. How many levels do we have now? And that second level, is it full? So is it stable? Okay, so we could either get to stability by getting rid of an electron to go down to the lower energy, or adding 7 more. Which one's easier? Carrying 1 electron away or carrying 7 new ones here? It's way easier to carry 1 bag of concrete and take it away than it is to carry 7 and add it, right? Okay. It's not gone forever. We're about to see where it goes. It does not just go forever because conservation exists. Okay, everybody agree that easier to get to stable by removing 1 rather than adding 7.
Would it be sodium?
So, good thought. Would it still be sodium? What did I move? Electrons. And what dictates whether we have sodium or not? Not electrons. Protons. I would never carry a proton away. That would change it. Absolutely. Okay, so the reason that we're hitting this is because we can see some reactivity with stuff, and it makes sense to why things react. Do you remember anything that I've told you about any of those elements? Hydrogen, lithium, sodium, potassium? Something with water. What happens when we throw them in water? They explode. That is a super violent, intense chemical reaction happening. They are super willing to react because anything in group 1, it only has 1 valence electron, right? Anything. They all do. They all willingly get rid of their 1 electron and give it to water in this case. And in that situation where they move down an energy level, they have all this extra energy that they have to get rid of. Okay, for this, we're not going to go crazy reactions here. I just want to make sure we talk about it. Do you want to see what one chemical reaction looks like just with dot diagrams? Okay, if I gave you a piece of sodium, would you put it in your mouth? That'd be a foolish choice. You shouldn't. What if I gave you chlorine gas? Would you put that in your mouth? No. Help me out here, though. We're going to see the utility of these, or the usefulness. So here's a quick example, usefulness of diagrams. And this is where we're heading, and this is like the last little piece. We're so close to being done. Okay, the next section, we will be doing more of these reactions and making sense of them. I just want to see a little bit of it first. Okay, I want to take the following chemical reaction. We're going to take a sodium, Na, and we're going to add to it a chlorine. And when they react, they form something new. Now, I can just write it, NaCl. Here it is. This is sodium chloride. Love it. What is this really, though?
Salt.
This is table salt. Okay, so if we think about the dot diagram structure, everything wants to be stable. Like the universe wants stability. It really does. Chemistry wants to be stable. That's the goal. I want to think about their dot diagrams. So here's sodium. Which group is sodium in?
The first one.
Okay, so how many valence electrons?
One.
So check this out. Here's sodium, and it has 1 electron. Plus, I'm going to combine this seemingly with chlorine. Find me chlorine on your table. 17. What's the ones digit? 7. So how many valence electrons?
8 or 7. but
7.
altogether.
So I'm going to do this backward from the way that I've been saying, and we'll see why here in a second. Okay, here's 7 of them. I've drawn them red so we can distinguish them easily. Okay, they want to be stable. That's the goal. Now, if they have to do something to get stable, I'm totally good with it, but they want to be stable. Is this stable yet?
No.
How come? It is not.
7 more.
Good. It needs 8 valence electrons. It needs to either add 7 or there's another option.
Just put that one down.
Get rid of 1, right?
Oh.
Okay, is chlorine stable right now? How many electrons does it have? Valence electrons?
77.
7, and what's it stable at?
8.
8. So it's also not stable, but now we just see the opposite side of it, right? I could either add an electron to it, or I can get rid of 7. Which one is easier? Adding a single electron. With this reaction, any suggestions on where chlorine might get its last and stable electron? From the sodium. Check this out. We're going to write little annotations down. The electron moves from sodium to where? To chlorine. And why would it do that?
To make it stable.
So both become stable. Okay.
How come the 7 electrons from chloride doesn't go to
So they could. They could conceivably, but just if you had to, I like the concrete example because it makes it seem so easy. Is it easier to move 1 electron or to move 7?
1?
That's like the answer because it's easier. It takes less energy. Okay, so here's what we're going to do. We need to move these. Now, I'm going to make one more comment. Before, we've just assumed that these things are electrically neutral, meaning same number of protons and the same number of neutrons. So they both have a charge of what if it's the same? So if sodium, for example, is 11, right? If right now it has 11 protons and 11 electrons, what's the overall charge? Neutral, give me a number. Everybody cool with saying it's 0? Okay, so everybody gets goofed up on this in math. We're going to physically move this one to here. And I'm going to show that in my next picture. So my next picture now becomes sodium. And I could draw all 8 of them because it kicked down a level. Or just leave it blank for now. I'm going to put brackets around it and we'll see why here in a second. Sodium plus chlorine. Now, this one is completely stable as well. So I'm just not going to draw those anymore. But here's where we're going to see a little connection to some algebra stuff. Let's say that you have a charge of 0. And from you, like overall, like sodium does, it's neutral. If I remove a negative, I've subtracted a negative charge, right? And now I would have 11 protons and how many electrons? If I got rid of 1 electron, 11 protons and how many electrons now? 10. What happens now if I have plus 11 and then a negative 10 charge? This becomes a positive, doesn't it? We removed a negative, which is the same thing as adding a positive. Minus a negative. You guys see in math all the time. This one was neutral, but it gained an extra electron, which means if it was a charge of 0 and I added 1 more negative, what's its new charge? Negative. Now here's where the magic happens. Positives and negatives, whether you're thinking electricity or magnetism, doesn't matter. They're opposites. And what do? They attract. And when they attract, due to these difference in charges, they stick together, and we now get NaCl, sodium chloride. It's the fact that the electron moves, and then they're both charged, and they attract. Okay, cool. This type of reaction has a name. We will go into this type of reaction much more in our next chapter. Cool. Feeling all right with it? Okay, anything from group 1 and 2, or I'll just set it here. Anything from group 1 really, really, really likes to give its single electron to something from which group? Louder. 17. Anything from group 1 will react really well with something from group 2. Anything from group 2 will react really well with something from which group? Why 3? So the 2 electrons need to move and fill in the 16. Yeah. So 2 and 16 react really well together. Okay. Now there's other combinations that we can look at and we will look at. But for now, as long as we're comfortable saying, hey, look, these electrons tell us how these things move and how they bond, we're going to go into the next chapter super easy. Okay. Last little piece. Remind me, what did I call group 18 yesterday? They don't react. They used to be called inert. There's a newer, fancier name. N. O. B. Noble. Okay, so for this, I'm not going to write it down. We'll hit it again. Group 18, they're called the noble gases. They do not react because, check it out, we can make sense of it now with our dot diagrams. Anything from group 18, doesn't matter what you're looking at. How many valence electrons? 8. And if it has 8 valence electrons, it's stable. If it's already stable, does it want to become unstable?
No.
It won't, it doesn't, hence the noble name. They are inert, they don't react with stuff. Okay, that is the end of our chapter. Okay, for this, we have a few things to do today. I am going to have you guys take the test tomorrow, specifically so that anybody who's in band doesn't have to wait 6 days to take it. So test is tomorrow. For this, it means we have a few things to do. First, what I want you to work on, you do get a little bit of homework. You get class time, and everybody's going to be working on this. Homework 16.3, you will find on page 416, and I'm going to verify these numbers. I want you to, ooh, how much math do you want? Yep, I can actually just go up now to there, but then I can write the other one. All right.
Oh yeah, we're doubling up on tests tomorrow.
Which other one?
Math.
Which one's harder? That's fair. Okay, 12 through 15. That's our homework. Beyond that, I have some other things. This is going to be due tomorrow. I'll take it at the start of class. We can talk about it afterward. Like, the test isn't super duper long. Other things that I want. This chapter is full of vocab. Okay. We have 23 minutes. You guys can finish these 4 questions, guaranteed. Like the next 10 minutes if you're working on it right now. Okay, beyond that, I have an additional thing that I'll give you. I have vocab review. That this is essentially going to be our practice test because it's almost all vocab. I want you to do vocab review tonight as well. I will give you a packet. Okay, tonight. This is going to go in as a take-home quiz. Obviously, you can work together because I can't stop you. Bless you. Don't chat GPT it. I don't trust chat GPT with really specific language stuff. Like jargon, I wouldn't trust it for vocab. Jargon is really special vocab for certain topics. So like if you go to an English teacher and ask, what's a quadratic? They probably won't know. But a math teacher would because that's language specific. Okay, and then other thing. I would encourage, I'm not going to require it because we have so much to do. You should probably make a note card. Okay, I want to stress, you need to know not the names necessarily, but you need to be able to replicate the timeline of our atomic theory. Know what Dalton's picture of an atom was, know what Rutherford and Bohr's picture were, and know what the modern picture is. You are going to have to draw little pictures.
Wait, was what's his name again?
John Dalton.
Oh, Dalton. Wasn't his just a dot?
Yes. You can use a note card if you'd like to make one. Cool. All right. So for now, I want you doing 16.3. When you're done, I'll give you the vocab and a note card. And you can do the vocab or the note card in class.
Are no cards required for the test?
I'm not going to require it because you have the other stuff. You should make one. Like, even if you don't use it, you should make one. Cool.
All the way. Jeez.